Thanks. Is this working? Yes, good. It doesn't sound as though it's working to me. Okay, thank you. Well, in fact, I've mellowed in the sense that the number of titles has gone down per talk, so to speak. The number of choices you have has gone down below one. It must be about a third now. I'm a little bit embarrassed. I was embarrassed last time I came to Berkeley by having forgotten what I talked on the time before. And it turned out that the time before then I talked about knots. And this time, that time I was talking about knots. And so I gave what was substantially the same talk on 2 successive visits to Berkeley. And this time I more or less have to give it because we're talking about knots. And so I'm going to give the same talk for the third time, which I think counts as 1/3 of a talk, so to speak. Okay. Well, I'm flattered to find that a lot of the terminology I introduced in my only paper on knots many years ago is now sort of standard. What I want to do, in particular, the term tangle, for what I always describe as a piece of knottiness with 4 ends, like that, so to speak. What I want to do, I've been thinking about the classification, enumeration of knots for a very long time, and I want to tell you, roughly speaking, what those thoughts have led to. Influenced very much, by the way, by the ideas of Bill Thurston more recently. Let me tell you what I'd like to do. I've despaired, and I think we can sort of say that we can now provably despair of understanding all knots. What we can do is do this hyperbolic structure, which gets practically all knots, and I'll ignore the rest for the moment. Using the sort of hyperbolic ideas, that reduces the classification problem for knots, let's say the equivalence problem for 2 knots, if they both have hyperbolic structures, to basically an isometry problem. You have 2 what are really finite combinatorial configurations with various distances marked on. This is not quite accurate, but it doesn't matter very much. And you just want to see whether this is the same shape as this. They might as well be polyhedra. Now, nobody is attempting to understand all polyhedra. In fact, as soon as you even talk about sort of enumerating polyhedra, you see it's a bit of a silly thing to do. And the only reason why people haven't yet reached that conclusion about knots is because there was something that made knots seem difficult as well. You see, polyhedra never seemed difficult. It just seemed sort of stupid to enumerate polyhedra. Now, with knots, we didn't know it was stupid until now. We haven't known. And now we know it is. So there's not really much point in trying to get some kind of notation or something that of a classificatory kind that actually distinguishes all knots, very, very clearly. What we can hope to do, however, is understand larger and larger and larger classes. And I like the idea of trying to describe a very large class in some kind of invariant terms so that we'll know exactly when 2 members of that particular class are equivalent. Now, the first class is, I think, the class of what I called algebraic knots a long time ago. I've been tentatively trying to change the name, but I don't know whether I'll succeed, to arithmetic knots. And let me just tell you on this blackboard, very quickly what they are. So we have the notion of tangle, and we can start with the 1 crossing tangles, of which there are just 2. This is crossing. These are the names I use for them, 1 and -1. But then we close under the operation of adding tangles. If this is t and this is u, then this is t plus u, where every now and then I sort of put serifs on this plus sign to indicate that it might not have all the properties that an ordinary plus sign has. So that's t plus u. And then there's also vertical addition, for which I don't actually want to bother with a special notation, but here it is. Start with these, or something very simple, and close under tangle addition, and you get the class of algebraic tangles. And then once you've got an algebraic tangle, do that to it, and you have an algebraic knot. Now, algebraic knots were completely classified by some of Stephenman's students, Caudron, Bonnerin, I don't know, certainly more than 20 years ago. I don't know that the proof has ever seen the light of day in print. If anybody knows about that, I'd like to hear about it. But I'll tell you in a moment what that classification is and then how to go further. Okay. Now, let me say something else. I want to understand things. I think we're still stuck in the 19th century, most of us, most of you. If we're using sort of ideas like Gauss's coding for knots, just walking around, that sort of is a sign to me that we've given up on the attempt at comprehension. Well, I think probably we have to, if we're talking about all knots. But I think we can really comprehend a very large class of knots, starting in particular with the algebraic ones. And comprehension means sort of finding mathematical structures in there that are like other structures that we know and love. Well, let me now proceed to ask for 4 volunteers and do some square dancing. Volunteer. Okay, you'll do, Jeff. Now, he's the only conscript. Come on, I want somebody else to really volunteer. He would probably have volunteered anyway. Okay, come on. 2 more. Okay. Great. So, whoops. No. Step in here. Okay. I think you two had better step down a little bit. Okay. And now, I want to tell you that... Oh, no, we're not going to do any skipping just yet. Whoops. I want to tell you that the tangle they're currently holding up is called 0. Oh, you know, I think we ought also to understand... Oh, yes. I don't actually have a good thing here for t plus 1 and t minus 1. Okay, so I'll draw them over here in unilluminated version. Could somebody switch on this light? That would be very useful. Great. So if that's the tangle T, then this is the tangle T plus 1. And the operation of going from T to T plus 1 is called twist them up. Now, what it means is that the person in this corner, who won't always be John Sullivan, swaps places with this one, who won't always be Jeff Weeks, by going outside him. Okay. Now, so that they've twisted them up. So now I've got to teach them how to display. The people nearest the blackboard raise their hands, and the others, okay, they displayed, okay, and you applaud whenever they display. And then you answer, and you don't applaud very long. You just, now you've got to tell me what this is. There's a test. This is 1. Okay, twist them up. This is now 2. Okay, if they displayed, so you go like that. One of those is good enough. Because they're not all that clever, are they? Okay. So it's 2, twist them up again. And twist them up again. Good. Okay, fine. That's great. Now, here's turn them round, which is, actually I'm going to change what this is later, but the particular definition I want to use just now is that. And this is minus 1 over t. So turn them around, you all walk one place clockwise. Okay, and you display, and they do their one clap. And now, what is this? Well, it's actually minus a quarter, because we were at 4. Okay, twist them up. Nope, that's turning them around you're doing. Nope. Twist them up. Now, what's this tangle? Okay. You know, if you don't display, they won't have to applaud. Okay, now they have to applaud you. Okay, so this, what is it, folks? 3/4. Twist them up. Where are we, somebody? 7/4. Twist them up. 11/4. Turn them around. Where are we? -4/11. Okay, I want you to get them home. You're only allowed to use these operations. And we're at -4/11. Turn them around, they said. So where are we? We're at 11/4. Oh, you're not allowed to twist them down. So turn them around again. Go on, turn them around. Okay. Now where are we? -4/11. Undo it, twist them up. As soon as you reach a consensus of what the orders is saying, we're at 7/11. Turn them around. Twist them up. -4/7. Twist them up, says somebody. Go on. 3/7. -7/3. -4/3. -1/3. Turn them around. +3. Turn them around again. -1/3. Twist them up. A display. All right. Now, incidentally, I want to do just one more thing. Turn them around. And now, where are we? Display. We're at infinity, which equals -infinity in this particular game. Okay, thank you. Okay, so what you've just seen is not just a correlation between certain. Oh yes. Now I won't be able to control that light. Let's try and do it without the lights for a time, if I may. Sorry, Joe. Somebody else can. That might be good enough. So these are some instances of rational tangles. Okay. Now you know there is a way of recognizing a rational tangle by looking at successive twists on the horizontal and vertical axes. So this one here has got 2 twists vertically and then 2 twists horizontally. So that means... Sorry? Oh yeah, okay. Thank you. I'll never remember all of that. This one here has 2 twists vertically. Let's have that finger there. And then 2 twists horizontally in the middle. That means in some way around it's 2.5. In fact, if they'd been on the horizontal axis, it would have been -2.5. That's this thing here. Because I've got -0.5 and I've added -2 to it. But it's on the vertical axis and, well, so it's 1/2.5, which is 2/5. In general, there's a simple little routine that you can do that says if you have A twists, let's say A twists on the horizontal axis with a suitable sign condition, and then inside that B twists on the vertical axis, and then C on the horizontal and D on the vertical, then what's actually happening is you get the rational number with continued fraction A plus 1/B plus 1/C plus 1/D and so on. And I did, in my old notation, prefer to keep the notation looking like the knot. And so I notated these by the sequence of partial quotients rather than the actual rational number. But I think conceptually it's easiest to use the rational number, although computationally that may mean that we have some little difficulty recognizing things. Now, what you've just seen is actually the action of a certain braid group. You see, we have some square dancers dancing, let's imagine that the tangle is sort of held inside a big ball. And then I have my square dancers like this, holding the four ends. Well, if, as they do that, the ball sort of sinks through the floor, and they're dancing around, a braid is being built up. This braid will record the history of the various twists them ups and turn them arounds that they've been doing. And so the four-string braid group acts on tangles. And in fact, it's the four-string spherical braid group, because they could be moving out. And that four-string braid group is very nice mathematically. It's essentially the same as the modular group of maps T goes to AT plus B over CT plus D. Let me just demonstrate that. Except that I must choose a different, I want to prove something. I must choose a slightly different 1 over T move. I'll need you again, my conscript. Oh, won't we need somebody over there? You better go over there. Whoops. Now what I have here, thank you, it's in display mode, is a general, good, it's a general tangle, okay? Now I'm going to introduce a new turn 'em around move, which isn't quite the same one as before. It'll avoid Jeff and I having to do too much dancing. Jeff, drop your top hand, the string from your top hand, and take that one instead. That's the new turn 'em around move, okay? Do it again, turn 'em around. It is actually different from the old one, but let's ignore the difference for the moment. We've just verified that its square is the identity. Okay? Let's call it gamma. Gamma squared is 1. Now, alpha I'm going to use for the adding 1 operation. And now I'm going to verify that alpha gamma all cubed is the identity. So there's an alpha. Now we do a gamma. Okay. Now I'm going to do an alpha. Now we do a gamma. And now we do an alpha. And now we do a gamma. And now we display and they all applaud. Okay? And what we've just done is verify that those two operations satisfy a well-known presentation for the modular group, the group of all T goes to AT plus B over CT plus Ds. So in other words, these names for the two operations, oh yes, I've used a slightly different one here again, but that one would work too, forgive me. These names for the two operations are, so to speak, legitimate. We won't make any errors because these two operations, let's call these alpha and gamma, these two operations do satisfy all the group theoretical relations that these two things satisfy. And so now I have an operation corresponding to any unimodular matrix here. Any matrix of integers A, B, C, D whose determinant is 1 can be regarded as a product of these two particular matrices here. And that's the modular group, PSL2 of the integers acting. And so that's a nice mathematical structure. And you know, one of the ways we make progress is by identifying things that have the same mathematical structure. So I'm going to think of those operations, those matrices, if we like, as braids that act on the tangle, or successive operators. There's something else I wanted to say about that. The four-string spherical braid group isn't precisely this group of matrices. It's 4 times as big. It's a group of order 2 squared. It's got a normal subgroup of order 2 squared, the 4 group here, which consists of the rotations through 180 degrees about the free coordinate axes. Now, I have a convention which I'll illustrate on this plate. The leading string comes in at the corner of this L. I call it the origin string. It's changed from what I used to call it, and for good reason, but never mind. This is the origin string. And then, if you go straight up, that line has slope infinity. So this string is called the infinity string. if you go straight across, this line has slope 0. That's the 0 string. And if you go diagonally, it's got slope 1, and that's the 1 string. So there's the way I name the 4 strings of a tangle. And you'll see that the operation I call infinity there, which is that, takes the starting string, which is the star string here, to the infinity string, and so on. Well, if I conscripted Jeff again, we could actually demonstrate that this is a normal subgroup. I'm not going to bother. If I say, do the infinity, if I conjugate the infinity operator here by adding 1, I'll find that it's the infinity operator. In other words, I subtract 1, which is twist them down, the operation I didn't let some people do, then do the infinity operator, which is rotating the place, and then add 1 again, you find you've rotated the place. And anyway, this is a normal 4 group. And what actually is happening is that the action of the modular group on this normal 4 group is got by reading mod 2. So if I want to know where infinity goes under some particular operator, AT plus B, 8 over CT plus D, infinity goes to A over C, and then I read A, and infinity is 1 over 0. So I stick T equals 1 and 1 equals 0, so to speak. And I'll get A over C. And then I read A and C mod 2, and that will tell me something. So I know, anyway, the complete structure of this group. Well, now, what happens when we come to knots? It turns out that there's a very, very nice, oh my, I don't seem to have structure. There's a very, very nice way of describing all the algebraic knots. And it describes them all in a sort of 1-1 fashion. And they're sort of compounds of bangles. So here is how I form a bangle. I'm going to take a rational tangle, and I hope you understand what they are now. They're the ones we've just been seeing, like -4/11. I take a rational tangle and substitute it for A, take another one, substitute it for B, and so on. The thing that I'll get if I sort of close up like that is called a bangle. Now, you know, there's not much point in having any of those tangles A, B, and C be integers, because an integer is just a twist in the bangle as a whole, and I've accounted for twists at the end there. And in view of the flipping move, it doesn't matter where the integers are. If I stuck an A here and then an integer, like say 2, and then C, I could spin these twists along until they're at the other side, and I'd get to A plus 2 plus C equals A plus C plus 2. So I can put all the integers at the end if I like, or I can absorb them. I mean, A plus, this is the fancy plus here, B plus 1 plus C is the same thing as A plus B plus C plus 1, because I can take this 1 off B, regard it as a twist, and pass it, and then stick it on C again. Well, what other symmetries are there of bangles? I can take a bangle and just turn it over, in which case, instead of being A plus B plus C, it would be ... plus C plus B plus A. Only, really, that's true if A is a rational number, because the 4 group, I forgot to say, the 4 group I was talking about, which consists of these rotations through 180 degrees, fixes all rational tangles. So as long as certain tangles are rational, I don't have to worry about these stupid little subscripts. But if A, B, and C were more general things, and if I turned it round, I would get A sub 1, sorry, A sub 0. Let me just try and find that previous slide a moment. You see, if I rotate about a vertical axis, I've got this operation here. Okay? So A plus B plus C is C naught plus B naught plus A naught when I close it off. Or I could rotate about an axis vertical to the plane of the paper, or various other axes. So what actually happens is, Bangles have only the obvious symmetries. I can cyclically permute A, B, and C, or I can apply this foregroup to the bangle as a whole. Now, if I want you to look up at that top thing there. If I apply the infinity operator, which is the rotation about this axis, to a thing made of rational tangles, it won't change it. But it's still acting, really. And that action will become important later. Okay. Well, now look. What happens if I take a braid like this, and well, this braid is represented by some matrix A, B, C, D. Now, suppose that the tangle I was applying it to was infinity. Then this will be that's the infinity tangle. Let me perhaps illustrate it a bit more clearly by doing that. In there is the infinity tangle. So if this is a certain braid B, then this object, which is a tangle, is A plus A, B, C, D acting on infinity, which is A infinity plus B over C infinity plus D, which is A over C. Now, what would happen if instead of closing it off at the bottom, I had closed it off at the top, is that I would get D over C. By exactly the same thing. The matrix I get reading it the other way is very like the transpose. I've forgotten what it is, but anyway, is D over C. And now, my great thought recently, a few years ago, to tell you the truth, is that since AD minus BC is 1 for any of these matrices, it suffices to indicate these two fractions. If I specify what these two fractions are, then I've actually told you what the braid is. That's not quite true. It's 2 to within the foregroup element. And so here's my new idea. Well, here's my few years old idea. It's called the Schizoid Notation. We have a bangle here, except that at a certain time, it just ends. And there are 4 places where we can't see anything, and then it carries on being a bit bangular and closes off. And then somewhere else there's another bangle which does much the same thing, but these are joined by a braid. Okay? So this is, say, big A, big B, big D, I suppose, and then here there's a big X and a big Y, if I can change my notation for tangles. Then what I think of this as, I think of this as A over C, and I think of this as D over C, except that there aren't actually these tangles. They're linked. There's some kind of link here. The braid in between them is completely specified by specifying these 2 rational numbers. And so I specify it like that by giving 2 rational numbers and indicating that they're linked. Okay? And then it's very, very beautiful what happens. As well as this, it turns out that I have to tell you where this string goes. Well, suppose in the braid it comes out here. And suppose this string comes out here. And this one comes out there. And this one comes out there. Then I indicate it in this manner. I say that the tangle I've just described, I'm sorry, which was A plus B plus, what was it? A over C, alpha, beta, gamma, delta, plus D, plus, that's one bangle. And the other bangle is X, I mean, there were some pluses, plus D over C, beta, gamma, alpha, delta, plus Y. Okay? So let me just repeat what I'm trying to say. If ever I have 2 bangles, except that, in fact, one of the things I'm treating as a rational number on one of them is really a braid that sort of starts there and goes to the other one, then I indicate it by just separating it off, this is why it's called the Schizoid Notation, into just two bangles, and decorating the two rational numbers with little Greek letters like this, which tell me where the strings go in and come out. Okay? And it turns out that that notation is, so to speak, one-for-one with the algebraic knots. Okay? Let me just try and sort of tell you what I mean. I think this is an absolutely wonderful discovery. So, you know, you should, if you're interested in algebraic knots, this is the way to think of them. An algebraic knot is just a collection of bangles, and a bangle can be notated as a sort of addition sum of fractions, okay, where it's only cyclically important. An algebraic knot is a collection of bangles, except that some of the rational numbers are correlated in pairs like this, and decorated with little Greek letters, and they really mean grades, ends of grades instead. And then it turns out that exactly the same equivalences hold for algebraic knots, for the bangles that make up algebraic knots, as if they were real bangles. So, for instance, I told you before that I could add 1 to big B here and subtract 1 from this thing that's now A over C. Well, you can still do that without any change. When you do it, you'll have to interchange the alpha and gamma, because that involved twisting two strings. I told you before that I could take this bangle and write it in reverse order. Well, if I did, I mean, if you did, so to speak, you'd have to write it like this. Here's D. Well, let's write it here. Here's D plus A over C, but now instead of alpha and beta being here, they'd be here. Plus B, etc. So the bangle I have at the top of the blackboard is the same as the bangle I have at the bottom of the blackboard. So so let me just repeat. You can take any set of bangles and link pairs of entries like this, provided AD is congruent to 1 mod C. Take the obvious symmetries of your bangles, which allow you to do things like adding 1 to one tangle in a bangle and subtracting 1 from the next one, or rotating the entire bangle either like this, or like this, or like the other thing, which I won't do because it would require doing a cartwheel. So there's a 4 group of symmetries, and the cyclic group of permutations on each bangle. And then you've also got to avoid certain stupid things. I told you before, none of the entries need be an integer. Okay? Well, it better not be an integer now. I mean, if you want to get the thing to be canonical. And again, the number of entries had better never be 2 or fewer, because if the number of entries is 2, then it really means that what's happening is this. I've got, what am I trying to say? Well, if they're just 2, I can compose. What it really means is that I've got a braid I think I'll ignore what I was about to say. It doesn't terribly much matter. There are certain trivial things that you're not allowed to do. You're not allowed to put an infinity in. You're not allowed to put an integer in. Every bangle must have at least 3 components. Subject to those trivial requirements, the notation is 1 for 1. And that's really very beautiful. A tremendous number of knots are algebraic. Now I want to move on to the ones that aren't algebraic and say rather quickly what we propose to do about them. Well, the algebraic knots are coped with by this Bangle notation and the Schizoid notation that I described informally. The next class, of which I hope to get a complete understanding, is what I call bracelets. And they're sort of analogous, except that instead of having 2 strings going along, we have 3 strings. Okay? And again, it's sensible to take any complete twists here, which you could have illustrated by making 3 adjacent tangles be 1. Take any complete twists and just call them twists and have them at the end. So this object is what I call a bracelet. Okay? Now, I should mention why I've written T or minus T at the end here. my plan is, I don't like negative numbers. I'm a very simple sort of mathematician. So if ever I wrote something with minus 17 twists up here, I feel, well, that's called minus 17 twistings up is plus 17 twistings down. So I allow myself to put the number of twists either at the top or at the bottom and change the sign. And it turns out to be very convenient. So when I write t or minus t, it means, you know, you can choose whichever you like and leave the other one off because it's indicated. Okay. Now, with bracelets, it turns out that I have a sort of conjectured algorithm that, you know, completely defines bracelets. It completely tests the equivalences of bracelets, except that the conjecture is false. It's false in a sort of rather trivial way at the moment, but I don't know how to cure it, and there may actually be no easy cure. But let me tell you what the algorithm is, because it's really rather nice. If you take a bracelet like that has just 6 tangles making it up, and I've drawn it here. You're supposed to join this end to this end. I haven't bothered to do that. I've also drawn it here, and I've also drawn it sketchily here. Each of the 6 tangles is this. This is actually an octahedron in 3 dimensions, if we like. One of the things I want to do, by the way, is get away from the idea of crossing number. Knots are not diagrams drawn on pieces of paper. They're in real 3-dimensional space, and I want to gradually work towards that somehow. Anyway, here is this octahedron. Now, an octahedron can be viewed as a bangle in 4 different ways. I can take this octahedron here and plunge my fist through the screen. I won't do it because it might annoy people. Plunge my fist through the screen, and then that becomes a bangle. But I could plunge my fist through any pair of opposite triangular faces of this octahedron. And so each bangle that has just 6 constituents like this has 4 names. Well, here it is. Its official notation is curly braces A, B, C, D, E, F sub 0. That's part of the general notation. But I want to just simplify that to pointy brackets A, B, C, D, E, F for a certain reason. Well, there are certain symmetries that we can see. Let's forget about those for a moment. But there's this other symmetry at the bottom here. A, B, C, D, E, F is actually equal to minus 1 over A, E, minus 1 over C, minus 1 over D. What that is the effect of taking my arm out of one of this pair of things and putting it in the other way around. Okay. Now, when I have the thing as a bracelet, what I can do is, if any consecutive entries are integers, then they actually constitute an ordinary braid. Look, here's an integer like 3, and then here's an integer minus 2, and then here's an integer 1, and I'm just building up a braid. Here's 4. That's a braid. Now, we completely understand the 3-string braid group, and so I can allow myself to replace this by any equivalent braid. Okay? And then, let's suppose, so whenever some of the adjacent entries in a bracelet are integers, let's lump them together and call that a braid. And then what we get is a sort of tangled braid. Well, literally. It's a collection of things which are alternately braids and tangles. Here's what we have. Here's a tangle. And then here's a braid. And then here's a tangle. And then we have another braid, and so on. That's what a general bracelet looks like. And I believe that its representation in that form is usually unique. Okay? If it's big enough, it's unique. And there are some small cases in which it's not unique, and one of them is this. If at any time you can so adjust these braids so that viewed in the bracelet form it has only 6 entries, then I can take it off my arm and put it on my arm again a different way. And you iterate those operations, and in all cases in which I've tried it, you just get a finite list of possibilities this way. And that's the algorithm to decide when 2 things are equal. Decide when 2 bracelets are equal. Almost. Okay. What actually happens, however, is that when the number of substituents gets very small, well, it turns out there are more symmetries. Now let me start introducing this figure. This perimeter here is the real axis. This is really the upper half plane, but I've imposed a Möbius transformation, so it looks like being a half of a disk. So this boundary is the real axis, and I've got a circle touching it at 0, and a circle touching it at infinity, and those two circles touch. And then whenever I have two circles, I can introduce a circle in between them. And in this way, the thing just sort of gradually completes. I'm trying to find a thing. I could, for instance, in here, well, 0 was 1 over 0. Sorry, 1 is 1 over 1, and 0 is 0 over 1. So I add those up and get 1 over 2. I use the median rule. So I add the numerators and add the denominators, and I see that that circle's labeled 2 over 3. Well, the modular group is the symmetry group of this horosphere packing in the upper half plane, which is a two-dimensional hyperbolic space. And that's the way I propose to look at the modular group. Whenever I draw a diagram, I want to understand what the special things are. And this gives me a visual picture of what the modular group does. Well, let me say something. If I put one of these tangles here equal to infinity, that diagram simplifies dramatically and becomes algebraic. Now, algebraic is indicated by red because it means they're completely solved, or alternatively, we've reduced the problem completely. Well, it turns out that in these diagrams, there are always a certain number of special values, unduly simple. Everything has only the symmetries that you can see if the substituents are complicated enough. But there are always some simple and therefore annoying substituents that complicate the matter. So in this case, these substituents make it go algebraic, and we just drop it from consideration. It turns out that always the ones in between make it have more symmetries. So if you substitute a 1 or a minus 1 in here, then, well, the tangle called A, B, C, D, E, F, if you put F equals 1, simplifies to this thing, and that's the definition of this object, and this is called a simplex knot. Let me write that this is a simplex knot. And I want to move, and that's also a simplex knot on the left-hand side. I want to tell you what happens, and I want to gradually try and acquaint you with the sort of philosophy of these things. Now, a simplex knot is what you get from the one skeleton of regular simplex, which can be viewed as sitting in three-dimensional spherical space, by substituting an algebraic tangle at each node. I'm only going to think of the tangles being substituted as rational tangles, just in order that I can make things simple. Basically, what that allows me to do is forget the little subscripts of infinity and 0 that tell me what's going on. So here's the definition of a particular kind of knot I'll call the simplex knot, A, B, C, D, E. Is the hex knot, in other words, the bracelet based on those parameters. It turns out to be simplest to change the numbers a little bit. And then, well, you know, the simplex has an S5 of symmetries. I can, if I allow reflections, if I don't allow reflections, it's only A5. I can permute those 5 nodes in any order I like. However, when I do so, I'll find myself permuting the 4 ends of them in various ways. And here's what happens. Oh, and I see that I forgot to define the operations called A plus, or X plus, is 1 minus 1 over, no, it's not. It's 1 over 1 minus X, and X minus is 1 minus 1 over X. I'll talk about those in just a moment. So up to the action of the modular group on these things, I can achieve any permutation. So I can put the tangles in the order B, A, C, D, C, E, D, provided I do those moves. Now that is I maintain, usually, these are the only equivalences there are. So in other words, every simplex knot has 120 names got by applying these transformations, which generate a group of S5 of permutations. I've always neglected, by the way, the dihedral group, which is there. So A, B, C, D, E is the same thing as B, C, D, E, A, And it's also the same thing as EDCBA. So 10 of the names are very, very easy to recognize. But there are, in fact, 120 because you can do all these moves. All we're doing is just rotating the simplex. Okay. However, now watch. I told you in the case of the bracelet knot, this thing here, that if you put A equals infinity, it becomes arithmetical, or algebraic, same word. And so it's still true that if you put A equals infinity in this, it becomes algebraic. But notice that I have somewhere here A minus appears. I'm sorry, somewhere here A minus appears. Now, this operation, God, I'm being a bit unclear, aren't I? This operation of rotating in this direction is the operation x plus, and rotating in that direction is the operation x minus. So what actually happens in the notation is this, that the various operators that were being applied at the top here, 1 over d you see is one of the operators, and this operator b plus, and so on, they are in fact the F3 that you can see in this diagram. Okay, 1 over a, for instance, is the reflection in this horizontal axis. Okay, so that would take 2 to 1 over 2. It would fix 1, interchange infinity and 0. So this is 1 over a. Let me try and write that. This operation is 1 over a, and this operation is 1 minus a. That fixes infinity and interchanges 0 and 1. And so it's obvious that these two operations generate an S3, which is something that may be familiar to you, and here are their products. This is 1 over 1 minus x, and this is 1 minus 1 over x. Are these two elements of order 3. So what am I trying to say? Well, I told you before that if you make any one of the substituents in this thing equal to infinity, you reduce to an algebraic knot. But therefore, it follows that if you make it be a 0 or a 1, you must reduce to an algebraic knot too, because this group I'm talking about is perfectly capable of changing infinity into 0 and 1. And so if you make any one of these three, put any one of these three special values in as one of your 5 entries, the thing will become algebraic. And similarly, it turns out that if you put any one of these 3 entries in, you get a reduction to a new kind of knot. Just as our hex knots reduce to simplex knots, our simplex knots will reduce to what I call quadruplex knots. And a quadruplex knot is built on this form. I didn't bother to say exactly what it was. Here is the definition of what pointy brackets A, B, C, D is as a bracelet. Well, once again, there are some symmetries of this thing, which are listed here. So everything has 16 names or something in this notation. So for instance, well, never mind. So if I give you 4 rational numbers, perhaps I better make it very clear what's going on here. These knots are specified, the simplex knots were specified by giving 5 rational numbers. Now I have a problem. Suppose I give you 2 sequences of 5 rational numbers. Are they the same knot? Okay? Well, the first thing is, I'm just repeating what I said because I found that I haven't been very clear, I think. The first thing is that any sequence of 5 rational numbers has 120 images under this group. So the names come in sets of 120 anyway, and there's no way of getting out of that. That's the symmetry group of the simplex. But then in addition, if you let any one of them be, you better not let any one of them be infinity 0 or 1, but if you let any of them have one of these 3 other special values, then it'll have more symmetries, and that makes it appropriate to consider it on this page instead, and then it's a quadruplex knot. Now in here, the same thing happens. Now it turns out that if we make any of these entries A, B, C, D be infinity or 0 or 1 or minus 1, it becomes algebraic. And those are the red circles here. And the blue circles in between, if we make any of them be 2, minus 2, a half, or minus a half, then it acquires extra symmetry and becomes what we call a triplex knot. And I want you to notice that 2 and minus 2 and a half and minus a half are really all the same thing. because there are symmetries of this knot that will replace A by minus 1 over A. So if A was 2, there's another name in which it's minus a half, and so on. So these 4 special entries are all one orbit under the obvious group, so they all do the same thing, and they reduce into what I'll call a triplex knot. Okay, and then we carry on. we now have certain triples of rational numbers, and we've got to decide when they're the same. There's the definition of a triplex knot in terms of the bracelet form. And now what happens is there are 5 values that make it reduce to an algebraic knot, and 5 values, the numbers are always the same, the numbers of red and blue circles, 5 values that make it reduce to a still simpler kind of knot. Now, this time, they're not all in the same orbit. And so, rather than invent 3 special kinds of brackets to go around the 2 rational numbers that are left, I employ a little code which has a certain mnemonic significance. So if one of the entries is 3 over 2, I don't think of it as a number. I just replace it by a plus or minus sign. That's just a code. Really stupid choice of notation, but that's it. If it's a half, I'll replace it by a plus sign. And if it's minus a half, I'll replace it by a minus sign. Then what happens is this, that, let me try and explain. So I get 3 different distinct kinds of duplex knots. Now, let me show you the bottom one first. This one is really 3 over 2 AB. Okay? And now, there's an identity for it. 3 over 2 AB is the same thing as 3 over 2 minus A minus B. Okay? So it's really either it's specified by a 2-component vector of rational numbers. It's A comma B is the same thing as minus A comma minus B. That's why I call it plus or minus. Okay? So plus or minus AB is the same thing as plus or minus minus A minus B. It's actually the mirror image of that, but I'm going to ignore it. And so the diagram for how things simplify has left-right symmetry here. If 1 is a special value, so is minus 1. Obviously, because if this has a name with 1 in it, this has a name with minus 1 in it. And then, it turns out once again, there are some values that give algebraic knots. These are the red ones. You can't really see the distinction between the colors because the focus is not too good. What am I trying to do? That's made it a bit better. So these values make it go algebraic. And these 6 values, which are really just 2 orbits of 3, make it reduce to what we might call a monoplex knot or something. It's only got 1 special entry. Okay, well, there's the identity. The extra symmetry that happens in this case is that A and B represent the same knot as minus A and minus B. In general, they don't. The extra symmetry that happens in the case when I put an entry equal to minus a half should be written somewhere. Yes, here it is. A comma B is the same as A super plus, let's call them A plus B minus, and it's also the same as A minus B plus. Now remember this operation, these are operations plus and minus, little elements of order 3. Plus means 1 over 1 minus t, which is an operation of order 3. So anything here has 3 different names. Okay? And correspondingly, the diagram has a 3-fold symmetry, which I'm afraid is obscured because I didn't draw it too symmetrically. But I can rotate infinity 0 to 1 to infinity symmetrically around here. And so now, if I substitute any one of these 6 special numbers, it goes algebraic, and substitute any one of the other 6 special numbers in between them, and it acquires extra symmetry. But effectively, substituting 3 over 2 is the same as substituting 1 over 3, and as substituting minus 2, because they form an orbit under this group. So really, there are only 2 different kinds of thing going on here. Okay, and then I get monoplex knots. Okay? And a similar thing happens here. Well, that's roughly speaking the end. So let me try and describe what's gone on here. I take the simplex knot. If I stick in infinity or naught or 1, it goes algebraic. And then we regard it as settled. If I stick in the other entries, -1, 2, and a half, it goes to what I'll call a quadruplex knot. Quadruplex knot. And if none of the entries is any of these 6 numbers, then I believe that there are no further symmetries than the obvious ones, the rotations of the simplex. It's a group order 120. Now again, in here, if I put in infinity, 0, 1, or -1, it'll go algebraic. If I stick in ±2 or ±1/2, it'll become a triplex knot. And the triplex knot, if I put in infinity, naught, ±1 or 2, it'll go algebraic. And if I stick in various other things, it goes to duplex knots, which have symmetries that the general triplex knot doesn't have. And then for each of these duplex knots, there's certain special values that will make it go algebraic, and certain others that make it down to monoplex knots. And then if I go still further, I get noplex knots, which are just knots. So what actually happens is I get one family of simplex knots, one family of quadruplex knots, one family of triplex knots, 3 families of duplex knots, which I just showed you. The next number is 7. There are 7 different types of monoplex knots. These were indicated by plus AB, minus AB, and plus or minus AB. These are indicated by notations like plus A, and so on. And then there are 22 particular knots down at the bottom of the string, for which really we can say that those 22 knots are the ones for which this notation is most inappropriate. Okay? And this, I believe, I've had no evidence to deny it now. It's been a conjecture I've had for more than 15 years, is the complete classification of simplex knots. Okay? Which is really rather nice. Then we have the analogous complete classification of, which I'm not going to describe because it's still wrong, of bracelets. But I just want to say one extra little thing before I go. What I'd like to do is try to get notations of this sort of kind for a very large class of knots. The algebraic class of knots is already very large, and I think it's scandalous that although they were completely classified more than 20 years ago, hardly anybody knows about them. And the notation for an algebraic knot is very, very easy, and the equivalences between them are obvious, and you should throw them away before you look at the remaining knots, if you're interested in classification problems. Well, I think you should do the same sort of things with the knots that I'm talking about now, and indeed with bracelet knots. Everything of up to 12 crossings is a bracelet knot with one exception, just one. Which at least, indeed, I don't even know that it's an exception, but it probably is. It's the 4-string hop flink. Now, here's a sort of modified bracelet knot. I've got 3 strings that are coming along and having tangles stuck between pairs of them in the bracelet manner. And then suddenly, I sort of stop being interested in this string and proceed to another triple of strings and connect them up like this. And I have a notation for this which works very smoothly, which is to introduce some curly braces in the middle of some other things to indicate that this has happened. Okay? Now, in terms of the language of basic polyhedra, which we've heard a little bit about this morning, this is a way of defining a whole slew of basic polyhedra in a uniform manner. And what happens, and they include all the ones up to 12 crossings, which is how I know my previous theorem. What happens here is that all the moves I was describing, all the equivalents I was describing for bracelet knots, can still be made to work for these bitty bracelets inside larger bracelets. And so we have, coming with this notation, the description of a large number of equivalences on it. I mean, this is the thing that I really want to do, by the way. I want to sort of have a notation such that lots and lots of the equivalences, preferably all of them, are visible in the notation. Okay? Of course, that often involves quite complicated transforms of the notation, but there should be some sort of easy thing to do that just works straight away in the notation. I don't mean just that your computer can work it out. I mean that you can work it out, or you can even sort of see them on site. Well, what happens here is all the equivalences I was describing between bracelets can be made to work between these little bits inside bracelets. And it's using those equivalences, it's fairly easy to prove my little thing about the 12 crossing knots being all bracelets, or almost all bracelets. Well, I don't know. I would love to collaborate with the people we were hearing from this morning and find out how many of all these, say, 15 crossing knots can be described as bracelets, say, and test the conjecture which is already false, but which might be corrected suitably, that all the equivalences of them can be got in a certain way. I mean, if we did that, and we proved that conjecture, I should say something about proof, we'd be able to just sort of understand that collection of knots. Or what I expect will happen, we heard, I think, that 32 particular knots were not hyperbolic. Okay? Well, I expect a sort of similar thing to happen. Out of these million knots, a few hundred will not be bracelets or something like that. Maybe it'll be a few thousand, I don't know. But whatever it is, I would like to say, well, okay, we've now done 95% of the knots up to this level. We've understood those. Now, what are the remaining equivalents that we need? I don't expect ever to understand all the equivalences this way, but I expect larger and larger classes. Let me just talk about proof, because I think we can prove the algorithm for simplex knots that I sketched over here. You see, the idea is this. If you put complicated enough constituents in, the thing will be provably hyperbolic. Okay? And I think that happens as soon as all the constituents are, as soon as none of the constituents are red in the diagrams I was indicating before. As soon as they're all blue or whatever other color you're using between the blues. Now, if none of them are blue, in other words, if none of them are that next class, that in-between class of special values, then I think what happens is that the shortest geodesics in the knot are actually inside the rational tangles. Okay? And so those rational tangles, the 5 shortest geodesics in the simplex knot, will actually be inside the rational tangles. And if we can prove that, then we've proved that the rational tangles are characteristic. The decomposition into 5 rational tangles is characteristic. And so what happens if you put one of the special values in? Well, you find that what the special values are really doing is sort of saying, this isn't really complicated enough. This thing's just sort of linking itself in some trivial way. And some geodesic becomes of equal, some geodesic in a rational tangle becomes of equal length to something outside. But then we have that the object has a different kind of symmetry, and you pass down to the smaller object and prove the corresponding theorem for it. So I think if you prove 1, 2, 3, 4, 5, 6, and 7 more, 13 theorems to the effect that if things are sufficiently complicated, then the shortest geodesics are in these rational tangles, then you will have proved the validity of this algorithm. And I suspect that the sort of enlarged algorithms, as I was talking about, the one that I'm saying is wrong for bracelet knots, can also be proved. And that would mean effectively that what we'd be doing is using Snappy, but doing it generically. In other words, for infinitely many knots, we would be able to say what the hyperbolic structure looks like in a characteristic way. So, I would like to sort of move on from the business of sort of feeling our way around these knots, getting hyperbolic structures, to being able to get a whole lot of hyperbolic structures at once. and decide all the equivalences between them. Well, I'm sorry, that's been a rather chaotic lecture. It must have finished by now, so it's finished.
Thank you, John. Let's invite a few questions from the audience.
We silenced them.
I can take the mic back to whoever wants to ask a question.
Nobody.
So,
do you think it's conceivable to build a recursive structure of these notations which would be able to handle larger and arbitrarily larger and larger classes?
That's the idea, yes. I mean, I don't mean recursive in the sense that you know what to do at each stage. I don't think we'll ever know what to do at each stage. That would, so to speak, be equivalent to solving the whole lot. And I don't think that's appropriate. No, but you see, I think that this simplex algorithm that I sketched in rather more detail than the rest is true and is provable, and one of you will prove it soon. In fact, I hope it's one or two particular people over there that will prove it, but never mind. But now, the next class, this bracelet class, and maybe you might have a different choice of next class to me, that's okay too. The current algorithm that I have and believed was correct for some time isn't quite correct. But okay, we build up some experience, see what the equivalences are, then I think we will be able to get a correct and complete algorithm for that. And then we sort of run it through, filter these enormous lists of millions of knots down to a few thousand, and try and see what makes them tick. I mean, I think this is the thing that I did a very long time ago when I produced my list of knots. I tried to impose a structure on it. Oh, not impose, but find what structure was really there. And in particular, I found this structure of rational tangles and so on. And that's really there. It's a natural feature of the knot structure. Well, I think at each level, you will find certain features. If you look, you sort of can understand most of the equivalences between these things, but then you see, oh, look, in this particular case, there's some additional move that you can do. And then you can sort of take the additional moves and erect them into an algorithm and proceed. In fact, I believe there's always an algorithm, and I think this is really proved. If you have anything that I call a cheese, you're supposed to think of Swiss cheese here. A cheese has a lot of little spherical holes, and those spherical holes are intended to contain tangles. So the little wires the cheesemaker put in the cheese as part of the cheesing procedure. Then, so 4 wires come through any sphere, and you plug in a tangle there. Now, I think there's a complete theory of any particular cheese. And moreover, I think this is proved. And the idea of it is what I said before. If you put complicated enough things in each hole, then the only symmetries of the whole knot will be these geometrical similarities of the cheese. In other words, this method of making it will be characteristic. And so what happens if the substituents aren't complicated enough? Well, take the first substituent, okay? There will only be finitely many values for it that aren't complicated enough. Say the values A, B, and C. Now stick A in, and you get an n-1 whole cheese. Stick B in, and you get a different n-1 whole cheese, and stick C in, and you get a different one. So now, inductively, any n-1 whole cheese has a complete theory, which is of this type. And so what happens is you get a tree of cheeses, but you see, as you put in the special values, the number of holes in the cheese is decreasing. So the bottom cheeses in the lot are just a finite list of knots. And so there is a potential algorithm for everything that you can get from one particular cheese. I don't think that's a sensible way of doing it, because I think you should lump different cheeses together. I mean, I don't have one cheese. I have this general bracelet cheese, which does an awful lot of things. But I think that, you can take any completely understood portion of knot theory and enlarge it and get a new completely understandable portion of knot theory. But you'll have to think in a different way each time. And that's my, the sensible way to treat it. You have to find out what it wants to be done. I mean, this discovery that the algebraic knots are just bangles surprised even me a few years ago. I thought they were more complicated, but an algebraic knot is just a finite set of bangles up to symmetries. Yeah. I'm sorry, I answered that too long. That'll frighten anybody else from it.
Any other questions?
No, go on.
Can you pass down the mic?
Is it possible to see if a knot is algebraic or the other kinds without looking at the projection from the three-dimensional picture of the knot?
No. You know, I said before I was trying to get away from projections, but I haven't succeeded. I freely admit it. But perhaps I should say something about getting away from things here. One of the things is the 120 renamings of a simplex knot, for instance. Many of them will have more crossings than the original simplex knot. So if you do the stupid thing of counting crossings, you won't see that they're equivalent. And I think that, you know, it's more conceptual to think of this thing as a simplex knot. But that was not an answer to your question at all. It's just a sort of remark. However, we then get another problem, which I didn't realize we'd have to solve. If we stop enumerating knots by crossing number, okay, then how do we relate our enumerations to previous enumerations? Okay, we have to find a formula for the crossing number of such and such. What is the crossing number of the general simplex knot? I don't know. It seems a tricky little problem. No, I don't know. I don't know any way that you can sort of guarantee to tell, do I? I suppose yes, there are complicated geometrical ways. I mean, there is an algorithmic way, I think, of telling whether something is algebraic. It's quite a complicated thing, and I'm not an expert on it. I don't think of a simplex knot. I don't have a particular way of drawing a simplex knot on paper. I mean, you know, I prefer to think of it as a simplex knot. You know, since that's what it really is.
Any other questions? Okay, if not, please join us for the reception outside, and let's thank Professor Conway again.